There is no doubt that the photonics is going to take a major role in the automotive ecosystems. And we hear very nice lectures, and we may realize that the role of the photonics in this, with its technologies, are very important to the automotive. So we will continue, and Mr. Matan Naftali leads the R&D team at Maradine in Israel. Maradine's innovation solutions serve as a core for head-up displays, exterior and interior lighting systems, laser headlamps, and LiDAR design for the automotive market. Mr. Naftali will speak on Maradine's lasers scanning solution based on MEMS technologies. Mr. Naftali, please.
Hi, my name is Matan. I'm the CEO of Maradine. In Maradine, we are making MEMS-based laser scanning solutions. With this technology, we enable the use of lasers to many different automotive products. I would like to share with you a short video showing some of the products we are working on. Who is Maradine? We founded Maradine in Israel in 2008 to enrich the world with our creative and unique MEMS technology. We operate in a fabless mode, utilizing the best of the world partners to manufacture our products. We are working around the globe with the worldwide leaders and Tier 1 companies. Ever since, Maradine have created significant IP portfolio and a value for many customers. One of Maradine's core competences are MEMS scanning micromirrors. We have 1D and 2D mirrors. Maradine mirrors could work in multiple scanning regimes and comes in different sizes. We believe that there is no one-size-fits-all solution for laser scanning. As a result, our mirrors are highly flexible, enabling us to support a variety of needs coming from our customers. To do that, we have the ability to modify the mirrors, starting from optical coating to a full custom design change. To support MEMS requirements, Maradine holds both analog and digital control schemes. The control schemes are highly innovative and use current state-of-the-art 2D feedback control loops. We have implementations of our controllers in discrete components and as IC for the analog controllers, and FPGA-based design for the digital controller. The combination of MEMS micromirrors together with controllers provides a high-quality scanning solution. In order to reduce time to market for our customers, Maradine provides a full picture-generating unit reference design. The reference design includes all it takes to design a laser projection unit: data flow, an API, a graphic user interface, and a proprietary timing algorithm implemented on FPGA, are completing an end-to-end scanning solution. To date, the reference design has been licensed to many customers, and a newly digital version is coming soon. Let me share with you a short video presenting how the MEMS micromirrors, controllers, and system firmware are combined together, providing high-quality images. 3 lasers are combined into a single beam. The MEMS micromirror scans the beam on a screen, pixel after pixel, very fast. Our eyes cannot see the fast scan and see a beautiful image. The MEMS movement is controlled by the controller, and a proprietary algorithm synchronizes the data going to the laser drivers with the MEMS position. To sum it up, whatever your product is, we can make it, providing your product with the wow effect of lasers, increasing your USP, all with the best thermal management and in a small form factor. Maradine is your ideal partner to automotive laser products. Thank you for your time. I will be happy to answer your questions now.
Okay, it's time for questions, please. You have a question on the chat. Can you read it?
Yeah. How small is small form factor of your components? I think just to get the reference of how big is a micromirror MEMS, this is a micromirror MEMS. It's less than 1 centimeter in tall and about half a centimeter in wide. That's the size of it.
What is the power limit of the lasers that you can use?
Well, laser power are for lighting applications are in the range of several watts, and this is something that could be withstand on such a tiny mirror, about less than 10 watts. For LiDAR applications like we've seen in this morning, it's more about a pulsed laser. So it could reach up to several of kilowatts, but the pulses are very short.
And what about the head-up displays? Can you provide enough power?
Absolutely, absolutely. For head-up displays, the laser power in the range of 0.6 to 0.7 watts for reaching enough brightness. And ballpark figure is for head-up display, automotive head-up display, is something like 10,000 nits. And this is something that could reach with such a low laser power.
Another questions? I think.
Can you state where you are manufacturing the MEMS mirrors? What are the current and future challenges for manufacturing, costs and size? Yes. Currently, we are manufacturing with partnership with Teleda and Dalsa in Canada, one of the biggest pure play foundries for MEMS and, of course, automotive certified partner. Future challenges in terms of manufacturing cost and size. It's a tricky. There is a tricky answer for that, because in MEMS, basically, let's say that below 10 millimeters mirror everything could be done. And there are a lot of things that needs to take into consideration when you are designing a MEMS micromirror, and the devil is in the details. You can have a large mirror for sensors like LiDARs, but then the dynamics is a little bit slow. Or you can have a small mirror for displays and lighting applications, and then the movement is very fast, so we can see a high resolution and a beautiful image. And you can play in between. It's highly depend on the how you design it. In terms of costs, we believe that you need to keep it simple in order for things to work well. Especially on the automotive market, you need to have high reliability in order to pass all qualification requirements. Having said that, it's something that needs to take into account a part of the design itself. And again, we believe in a lot of in a very sophisticated design, but very simple processing. So a simple processing will affect the cost, will affect the yield, and also the reliability at the end of the day. Eitan asks, what kind of optic implementation do you use, free space or PIC? Both. We are using both. As seen at the presentation, Maradine is providing the scanning solution, but we are partnering together with the laser and optics providers. And some of them are using PICs and some of them are using free space optics. As long as the laser beam hits the MEMS, it's good for us. Is your focus on MEMS only or the applications you mentioned? Well, Maradine is focuses on a scanning solution. As said, we are providing a full scanning solution, incorporating the MEMS controllers and software layer in which we are synchronizing the MEMS position to other components within the application, either laser drivers or sensors. And we are at this level, we are not focusing on the application level.
Okay, Matan, I think that you are provide so much interest. So only two questions more, and the later you shall ask Matan directly.
So with pleasure. So
after the conference.
Yes, Santiago asked, what about shock and vibration? Is there a limit? Have they been tested in automotive environments or certified somehow? Yes, absolutely. There is a limit like to every material, but we are working and testing all our MEMS according to automotive requirements, AECQ 100. There are several of automotive cases there that we test both for shocks and vibrations.
Okay, and the last one? If you cannot see, may I ask the last one? Would you consider to incorporate it in the eyeglasses?
Absolutely. Maradine is operating in the automotive market, but also very strongly within the AR/VR display market. We are working closely with leaders in the consumer electronic markets to implement such a technology into smart glasses display.
Okay, Matan, thank you very much. Very interesting, and keep in touch.
A pleasure. Thank you very much.
Okay, we'll go to the next one. Dr. Eduardo Margallo is the CEO of Omatidia LiDAR in Spain. Omatidia, I hope that I pronounce it well. Omatidia LiDAR is developing a new generation of optical ranging sensors. Dr. Margallo will speak on light field sensor, a breakthrough for high resolution, long range 3D imaging. Dr. Margalio, please.
Hello from Madrid, and thanks a lot to the organizers of OpTecBB for the opportunity to present on Material LiDAR. We are a new venture in the field of optical and 3D imaging that is bringing to market a new type of sensor, the light field sensor, which is a breakthrough for high-resolution, long-range 3D image acquisition. Our concept is based actually on the compound eye of insects, which break the problem of recognizing the objects in their surroundings by using a large number of elements, and that's exactly what we do. We are all familiar with LiDAR, and it's basically a technique that provides information about the distance to the different objects, not just the color or the light intensity coming back from them, but really the distance. This is, of course, very important in many applications, including autonomous driving. However, when we looked at LiDAR for the first time, we realized that there were still important challenges to be addressed, especially if you try to do long range and high resolution at the same time. You hit a number of significant trade-offs that limit the performance of the systems or increase the complexity. When you analyze it, you realize that this trade-off is actually coming from the amount of light available for the imaging problem. And the reality is that all imaging algorithms for LiDAR, all principles, are based on filtering light very aggressively. In time of flight, light is concentrated in a pulse which has a duration of less than 1 nanosecond. And in FMCW LiDAR, which has continuous wave, which allows you to put more power in average, the problem is that you need to put all your light into one direction only, which again, because of high safety considerations, limits the average power you can emit. This limitation in the number of photons is in reality what limits the performance of LiDAR systems today. We are trying to break that limitation, that trade-off, by developing a new type of sensor. Our light field sensor collects the light coming from the scene and measures both amplitude and phase at each point. And through the combination of all these measurements, we are able to reconstruct the direction and the distance the light is coming from independently. This is not unlike what you see in nature. If we compare our sensor generations to different types of sensors, we see a similar evolution to the one that you see in the natural world. Ants, which are essentially 2D insects, can live with a few hundreds of elements. Then flying insects, which are 3D, need an increasing amount of them, to the limit where you see dragonflies, which are predators and need to hunt other insects in flight. They reach close to 320,000 elements. Our generations follow a similar trend. So the first generation of devices we have created has 512 outputs and provides us with very high quality images in 2D, so along a plane. Now we have the second generation that is being integrated with up to 50,000 outputs, and that's providing already 3D imaging quality. And we have a third generation now being prepared with up to 500,000 outputs. And throughout these generations, and as we will see also in combination with the source, we are able to get to resolutions which range from 1 to 10 million points per scene video rate and more than 300 meter range. I mentioned before that the problem was insufficient light. So the sensor is an enabler for us to provide more power to the imaging problem. But of course, we need a source that is able to match that. And we have developed an arrayed source with an output power close to 1 watt, which is inherently safe, even though that 1 watt is indeed continuous wave. This is actually what is needed, even with an instrument as sophisticated as the human eye. The output power, optical output power of the headlights of our cars is about 5 watts. So it's hard to imagine you can really do high quality long range imaging with just a few milliwatts of optical output. We are using this technology for different generations of products. The first product, which is based on our 2D chip, is being applied to a 3D metrology scanner. which is able to provide down to 10 micron distance resolution and reach several tens of meters, above 50 meters with that resolution. It has applications in industrial metrology, telecommunications, aerospace, and civil engineering, and is expected to hit the market later this year. On the other hand, we have another generation of products coming, which is based on a 3D sensor already. You have a picture of the sensor with the readout there and the optical fiber. We expect to have laboratory results on the sensor still this quarter, and hopefully some integrated prototypes towards the end of the year. Here we are targeting more standard LiDAR applications like autonomous vehicles, AGVs, and high fidelity augmented reality and virtual reality. So our positioning as a company is in the intersect between flood illumination, so really putting light into the whole scene in parallel, and continuous wave. Thanks to our proprietary sensor architecture, we are able to combine these two features in a unique way, allowing us to increase the optical power available, and from that we derive very high resolution, sensitivity, and range. In terms of markets, we are focused on the railway market, where we have a number of projects planned for both rolling stock and infrastructure. The space market, where we have a running project on metrology of large deployable structures with the European Space Agency, and down the road also automotive and some other high volume markets. We're currently open and interested in exploring collaborations with application partners. So I'll be happy to take your questions, of course, and discuss further offline. Thank you.
All right. It's a question time, so please. Dr. Margallo, would you like to say things more? So you will get you have a chance now to address some topics and elaborate on it.
There is one question from Frank. What will be the size of your automotive grade systems?
Hello, Frank. Thanks for the question. The size of the sensor is really small. It's the size of a CMOS emitter. Of course, all the electronics around it, really to be able to extract the data and provide it in a standard format will increase the size a little bit. We are looking at the target form factor of a cube of 10 centimeters or slightly less.
Any more questions? Well, Dr. Margallo, thank you very much.
One more.
Oh, Marv, please go ahead.
Maybe you could provide a little bit more technical insight into your sensor.
Yeah, our sensor can be assimilated to those coming from the world of radar to massively scaled version of MIMO radar. So basically, we are able to collect the field impinging on the sensor through an array of antennas, and we measure both phase and amplitude. So we're able to combine them digitally to recover the scene, and we enrich that with an array source where we can also apply orthogonal coding to the outputs of the emitters. So that gives us virtual arrays which are really very high resolution, and also it allows us to increase optical power because each of the individual elements in the output will not be, let's say, collimated, cannot be, let's say, refocused onto a single spot.
More questions?
Yes, there is one more in the chat.
Oh, can you elaborate a bit on other application fields, pros, cons of your sensor?
Sure. We've got started on applications in metrology. So really looking at very large structures like bridges and large antennas in space and telecom. Because here we can provide extreme accuracy and really image very large structures, right? Also the resolution can be leveraged. We think that automotive is also an ideal market for us, especially when you're looking at, let's say, the use cases where this combination of long range and high resolution is of value. And of course, robotics, I mean, that's kind of an intermediate point where, well, yeah, I mean, range and resolution balance is a little bit different, but still it can profit from the innovation we bring. In terms of pros and cons of the sensor, I think the sensor has a lot of pros. It can do things that you cannot do otherwise. One of the main challenges, I wouldn't say it's a con, but one of the main challenges we faced is actually dealing with volume of data, because these arrayed receivers can potentially generate a huge amount of data, right? If you look at each one of them as an FMCW receiver, clearly the aggregated output is very large. So something we've come up with, and which we are now fully integrating, is a photonic processing scheme, really to be able to bring all of this information to baseband, leveraging the sparsity of the matrix.
Okay, more questions? Okay. Thank you very much. Thank you very much, Dr. Margalio. And we'll go to the next one. Thanks. Dr. Santiago Royo is the Vice President of Business Development at Beam Imaging SL in Barcelona, Spain. Dr. Royo will speak on 3D perception unit for embedded data fusion of LiDAR and 2D images. So, Dr. Royo, please.
Hello, good morning, everybody. I'm Santiago Royo, I'm from Imagine, and I'm here to present you very briefly the capabilities that we've been developing regarding the manufacturing of perception units, which include not only 3D LiDAR, but also every type of 2D imager you may imagine, and including data fusion, so correspondence of each point cloud with each image are established by default inside of the camera with embedded computing. Everything started with LiDAR some years ago, so I believe the best way to start is with our LiDAR, which is extremely high resolution. It's a solid state approach, it's a raw data, it's not processed. With cameras and train artificial intelligent algorithms. For that, our proposal was to develop a system which was RGB camera and LiDAR fusing each point in the point cloud with the corresponding 2D image. You may see that if we implement this, you may see that you can do it in real time, okay? You may have the superposition of the point cloud with the RGB information in every moment of the scene, perfectly synchronized at different levels of resolution. You may see that it's a 2 centimeters, 3 centimeters wide bar here, and you may see how data is completely fused. So you can transfer your 2D information or your 2D processing onto the 3D point cloud, or conversely, as you prefer, making it extremely easy to train your AI. This worked very well along different development programs we've been working. We've done that with polarimetric imagers, we've done that with thermal imagers, with a number of imagers. So essentially, now what we've been working in the development of a general purpose unit, which is what we are about to launch. We're certifying that as a product in the coming weeks. And well, this is the spec of the LiDAR, which looks large, but it's 10 by 17 by 15, so it's small. It has all the features of the high resolution LiDAR imager that I showed you before. It has 460 by 150 pixels, and it has 0.13 by 0.13 degrees of spatial resolution, which is highly dense, which is especially good if you want to do detection and if you want to do classification along distances, which is what you normally want to do with an autonomous vehicle, sorry. Then, of course, this is the spec of the LiDAR, but we've added inside of the product a camera, an RGB camera, which is already embedded, and a thermal imager, which is also already embedded. So we are able to fuse the data of all these imaging modes in a general purpose product and provide it off the shelf to any of you who are interested in that. We also can do things regarding adding here a polarimetric imager. There's a way to manage to add a polarimetric imager plus the RGB data, which brings on a system which can deliver up to 13 imaging modes, which of course can be tailored. If you don't want the thermal, we take the thermal out. If you don't want the polarimetric, we take the polarimetric out. We can manage to have up to 13 imaging modes fused with the 3D and RGB, 3D plus thermal, CCTV plus thermal, 3D plus CCTV plus thermal, whatever you want, including polarimetric imaging, which may have sense in particular applications. We found that in given environments it's very, very useful to have polarimetric angle of polarization or linear of degree of polarization, which makes an overview, a fast overview of what can we do. We have also learned that we are very, very good managing to integrate this type of systems. So if you want to build your autonomous systems and you want to have your perception unit integrated on someone, by someone, I think we can be the right approach. So here you have our emails, our contacts, and it will be my pleasure to ask any questions or to begin any B2B match you want to join afterwards. Thank you very much for your time.
Okay, thank you very much, Dr. Ariel. It's time for your questions, please. So you got a question from Omer Cohen. What is the purpose of using all the sensors together?
The purpose is that you are able to work with any of the AI detection capabilities you may need. When you want to work with AI, for instance, working with 3D point clouds, maybe something which is difficult from the point of view of training the network and so on, that's starting to be developed, but not the best approach. But you can work either with the 3D point clouds, or if your detection is on 3D, or you can work with the 2D, and then as far as you have the information already fused, you can transfer both of the signals from one side, both the information from one side to the other. So you can select which is the best option. For instance, if you want to go very far away, it's very difficult to have a lot of points, even if we work in high resolution mode, as we are doing, we work with 400 by 200 pixels, which is what I was saying in the video, which I'm sorry, it was not heard, because it worked in my PC, so I'm sorry for that. When we do work with given applications, working very, very far away, for instance, you hardly have any data points where you can manage to have, in the 100 meters, even working with high resolution, you don't have enough information. And you can have that with the camera. So depending on the type of application you want to develop, you can work a lot. And you can take a lot of advantage of having the different imaging modes. In fact, all autonomous cars are working with 3 or 4 different imaging modes currently.
Okay, more questions? In any case, you may be in contact with Dr. Royo later. He provides his addresses. So thank you again, Dr. Royo. I will continue.
Thank you very much.
Thank you. Dr. Ofer David is the CEO and co-founder of Brightway Vision in Israel. Dr. David will speak on gate vision, clear, complete, homogeneous, long-range imaging, driving clarity in darkness and all weather conditions. Dr. David, please.
Shalom and hello everybody. I'm Ofer David. I'm the CEO and co-founder of Brightway Vision. I would like to thank the Photonics Association for inviting me to present our technology. Brightway Vision developed a product called Wisdom. It's a camera system to allow imaging at harsh weather conditions at nighttime based on gated vision. What we actually provide is a module. The module contains a very special CMOS sensor that we've developed, and we produce it here in Israel in Tower Semiconductors, and a gated laser. The thing that is special about this sensor is the ability to turn it on and off rapidly in terms of tens of nanoseconds without losing the photocharges that have been collected. In order to see how the product looks like on a car, you can see it here, where you see that our laser is incorporated into those daytime running lights here, or inside the headlamp here, or behind the windshield, and the camera is installed behind the windshield in both cases. A new version that will come out is where the laser is incorporated as in the daytime running light of the headlight of a car. And how does it work? Let's see what is actually behind it. So it's similar to a radar. We emit a pulse of light. We collect the reflections. We keep the camera closed for some time. We allow the pulse to propagate, and then we open the camera to get echoes at specific ranges. And this is pre-programmed, and therefore we can predetermine the ranges that we want to image. If you have a scenario, for example, like I'm showing here, where you have a pedestrian, you have a cyclist, and you have a car at different ranges, we create several frames where each frame actually is a specific slice of the range. We call it slice because we actually take the range and we slice it to bits. And just for the sake of this example, we're showing 4 frames. Arbitrary, we can change the ranges on the fly from frame to frame. But if I create an image from 20 to 50 meters, it will allow me to see the pedestrian with no background behind it. And this is true for day and night. And I can also create an image which combines all those sub-exposures together and provide you a nice image from 0 to 250 meters. Let's see some examples. So here on the right, you see a reference camera. It's not a cell phone camera, it's a slightly better camera. And on the left side, you see our gated vision. And actually, three things to note out in this example. First of all is the range. We're able to see to 300 meters, and this is due to limitations of size and eye safety. You have to be class 1 in order to be on a car. And the second thing I wanted you to notice is that we are not blinded by the oncoming traffic with the headlamps on. And the third thing, which I want to note out, is that the brightness in the short range and the brightness at the long range is the same brightness, although you would expect, like you see in the visible camera, a drop in intensity. Let's see a video as an example. So again, you see the nice image to 300 meters and more. You see that we are not affected by the headlamps. The image is clear. You see exactly what you want to see in an automotive environment. And this is the first example. This is clear weather nighttime. Another example is under fog. Those two images were taken the same time. It's actually part of a study that was done by Mercedes. They've published a paper about it. And what you see here is that we are not affected by the backscatter. And why is that important? Under fog conditions, you have two actually limitations. First of all is the power, because the fog is a scattering media, so very little power will reach the target, and also very little power that is reflected from the target will reach the camera. So you can overcome that with a very strong laser. But this is not enough. You have to do another thing, because if you use a very strong laser, you will be blinded by the short range back reflections. The droplets at the short range will reflect the light in such a way that it will bring you to another limitation, which is the contrast. And therefore, you will not be able to see the target, not because you don't have enough energy there, just because you lost the contrast. Another example, a little bit longer, a fog chamber which is a little bit longer. By the way, 2020 was a bad year for us for fog chambers because we were not able to travel, and unfortunately there is no fog chamber in Israel. There could have been one. There is the technology, there is the space, and is even funding, but we couldn't bring all the parties together to create a fog chamber in Israel. So this example is coming from Japan, and you see that we are able, with gated imaging, we're able to overcome the backscatter, use enough energy to image the range that we want, and gets the good contrast that you see in this image. And if using a regular camera, of course, you're blinded. And if I was using high beam, this is an example where we're using low beam. But using high beam, the situation would even be worse because the backscatter would be worse. Another feature of gated vision that I want to show you is a depth map, or a colored depth map, as you see here in this image. This is one of the test vehicles that we have with Mercedes. Our system is installed on it, and let's see this video, because I want to show you, first of all, at the bottom you see the three slices that we're using: the short range, medium range, and long range. Let's stop the video here for a minute, and here you see the reference camera coming from Mercedes, and on the left side here you see the depth map. You actually, blue stands for short range and red stands for the long range. And what you can clearly see is that out of the three slices that we created here, we have quite a reasonable depth map. The accuracy that we have today is 80 centimeters 1 sigma, which is nice, and that comes on top of a very good image. For instance, if you want to see this pedestrian, it will be very difficult for you to see the pedestrian, whereas in the gated vision you see it clearly. Let's see the video again till the end, because there's a nice example there. So the car is traveling in the street. You have a very nice image. You have also some information about the range. We are following a bus. The bus will stop, people will get off the bus, and then it will be nice to see the ability to see the pedestrians, as you see here, crossing the road, and there is no chance for a regular camera to resolve the pedestrians which are walking. There's too much clutter at the background, and this is why it's impossible to see them. In order to cover weather conditions, let's also look at snow. So we saw rain, we saw fog, now we see snow. As you see here, again, the three slices, short range, medium range, and long range. And this is the full image. You have full situational awareness, whereas a regular camera will fail. So I think we covered the bad weather. What I want to show here is the ability to use it with AI. This is an example that we fed the same computer, the same algorithm was used from both images. The only difference was the input. And it just goes to show that if you have a good input, you will have also a good output. So the RGB camera did not produce enough information for the algorithm to capture anything, to detect anything. And as you see with the gated vision, it was the algorithm was working very well. I mentioned the ability to see retroreflectors, and this is an important feature in automotive because all cars must have retroreflectors at the rear end, and we can differentiate between diffuse reflectivity and retroreflectivity, and therefore give additional information about targets, and actually also reduce the false positives if needed. Our system is also used to detect very small targets, what is called lost cargo on the road. And this is thanks to the special way that the system is installed on the car, because the headlamps are installed very low, the camera is installed in the windshield, so we are hitting actually the road in a very shallow angle, and therefore anything, the road itself will reflect very little, but anything that stands out from the road will immediately have a very good contrast compared to the background that it has, the immediate background of the road. And that's what you see here as an example. So up till now we saw some examples of gated vision. I've showed you that the image is very good under darkness and harsh weather conditions. We offering our system in 3 segments. The first segment is ADAS, Advanced Driver Assistance Systems. The second one is for autonomous vehicle, a little bit higher performance. And the third one is for light rail, where we have our first serial production, and we have started deliveries in this market. It's a similar system, same sensor is used, but the system itself is a little bit different between segment to segment. We have some time for Q&A, and I'll be happy to answer any questions that the audience might have.
Okay. Ladies and gentlemen, it's your time now. Ofer, you have questions on the chat, I believe.
Looking at it now. What would be the size of your automotive grade system? Well, actually, we should have had a system here on my table, but it's the camera is the size of a fist approximately, with the lens and the illuminator. I will just use my hands because that's the best example I can think of showing you the size. Is about the size which fits into a regular headlamp or daytime running light. So that was the first question. Can you elaborate a bit on other application fields of your sensor? Yes, so actually it's a good question because we have started now expanding a little bit our offering to other markets. So special duty vehicles, light rail is the first place where we have serial orders, but also we are now opening it for maritime and security applications. and in the security application, the advantage might be if you want to create a virtual fence. So you can actually create an area, one slice, and then you can decide I'm looking only for targets which are moving in this slice. Anything beyond or in front of this slice is being ignored because the system will not see it. So that will reduce the load of filtering out systems. And of course, if you want to see during harsh weather conditions, that's where we excel. Oh, somebody wrote that he cannot hear me, but I hope that you can hear me.
Yes, we can hear you very clearly.
Okay, so there's a false negative here. The second question I'm answering now is what is the wavelength that we are using? And the wavelength is near infrared. It's in the 808 nanometers. The third question that I have here, how does it work when all cars have the gated imaging? Oh, that's a very good one. Actually, the duty cycle of ours, I'll repeat the question in full. How does it work when all cars have gated imaging flashes on the roads? So beside the depth map that we are we haven't finalized the solution, we are still working on it. All the other applications, actually, we have a very nice solution. The duty cycle of the system is very low. It's a one-digit percentage, lower than 5% in many cases. And therefore, we allow other systems to work when the other system is not working. And there's a way that the system recognizes when other systems are in the same region. So that is the case here. We're not working continuously. We're working only in a very short duty cycle. The next question that I have here, hi, is it all already qualified? So by the end of yes, it's during qualification at the moment. The ACQ 100 for the sensor and the ACQ 102 for the laser source. And it will be, according to plan, it will be qualified by the end of the year. And let's see if we have something on the chat. What is the limit of your system? What can you not see? Oh, that's also a very nice question. So I would not recommend anyone to walk with a diving suit on the road, because a diving suit has close to zero reflectivity at nighttime, at 808 nanometers, sorry, not at nighttime, at 808 nanometers. Also, tires. Actually, new tires have a lower reflectivity than used tires. Used tires have 5% or so, maybe a little bit less. But we found a way to detect the shadow. We have, now that we filed for a patent, I can talk about it freely. And we will have probably a video in the next conference that Shlomo will arrange. We'll probably have a video about that. So we are able to detect the shadow that it creates on the road. So we're creating a shadow detection. Imagine that you have two headlamps, you're flashing them in sequence, and then you're moving the shadow on the road. That's the way that we can detect things that are with very low reflectivity at 808. The next question that I have here, what is the frame rate of the 3D point cloud? Okay, good one. So the overall frame rate of the system is 120 hertz. Usually we use 3 slices and 1 full image. So the depth map would be 30 hertz because you need the 3 slices in order to cover the full depth map.
All right, I think that you draw a lot of intention.
Thank you.
And if you are looking for collaboration, oh, there are other questions, please. Someone wants to ask question? Okay, so if you look, you want to collaborate with other partners, the technological collaboration, don't hesitate to call us.
No, definitely no. I saw some very potential collaborations there during the day. Thank you.
All right. Thank you very much. Thank you very much. We will go to the next one. Mr. Thomas Huntke has been part of Jabil Germany optics teams for 15 years. Mr. Huntke will speak on imaging systems for automotive applications. Mr. Huntke, please.
Hello everybody, and thank you very much for inviting me to this meeting. My name is Thomas Huntke and I'm from Jabil Optics Germany, and I would like to give you an overview about automotive projection systems. Let me share my screen with you and let me start my talk now. First of all, I would like to give you a short overview about Jabil and what we can contribute to the topic of projection around the automobile. Since Jabil is a manufacturing service company and not a product company, you are probably not familiar with Jabil because you don't find this as a brand in any shop or supermarket. However, Jabil is one of the largest manufacturing service provider operating in various fields. This includes consumer electronics, automotive and transportation, healthcare, packaging, and connected devices. Jabil itself has more than 240,000 employees at more than 100 locations all over the world. Last year, Jabil closed with a record revenue of $27.3 billion. But Jabil is not only a manufacturing company. Besides manufacturing service, we offer product, process, and equipment design for mass productions. This includes full product design, optomechanical design, development and integration, industrialization, and deployment of products for the serial production. For Jabil Optics, this applies especially for projection imaging systems, which are used in the following applications: augmented and virtual reality systems, LiDAR, 3D sensors, and advanced camera systems. Jabil Optics sites are mainly based in Jena, Germany. This is where I'm coming from. But we have also a site in Burlington, USA, where our group for active alignment is located. And we have sites in Guangzhou, China, in Taipei, Taiwan, supporting NPI activities and transfer into mass production. Now I would like to talk about our automotive optics capabilities. As mentioned before, one of the design sites of Jabil Optics is based in Jena, Germany. And this is where I'm coming from. We started in 1996 as a department of the Carl Zeiss company with designing optical modules for the Texas Instruments DLP technology, which is a mirror chip that reflects the light onto the wall or into the surroundings. With this mirror chip, it is possible to build optical modules for different types of projectors, rear projection TVs, head-up displays, as well as a lot of other applications. With the transition to Jabil in 2006, we became the Optical Competence Center of Jabil, supporting all optical device design activities within Jabil. On this slide here, you see some of the pregnant design examples. For instance here, this is one of the first optical modules for DLP we started with. Then our focus was in the rear projection TV. This is an optical engine we designed. What you see here is a camera system with a very tiny camera of 15 by 15 millimeter, designed for life science application and endoscope application. In the last year, our focus was mainly on LiDAR. Our projection experience, of course, is not only limited to DLP technology. We have also experience with LCOS systems. Here we have designed a very comprehensive near-to-eye application. On MEMS systems, we have worked on a 3D sensing application, what you can see here on top of the module, and MEMS is also used in the LiDAR. As already mentioned, here are two examples for DLP technology. One is a Pico projector that has been integrated in a Samsung mobile phone, the so-called Samsung Galaxy Beam. In addition, we also have experience with micro LED and OLED, for instance, for virtual reality goggles. On the next 3 slides, I would like to give you some automotive-related design examples. Number 1 is our laser matrix headlight demonstrator. The application is an automotive headlight with a glare-free high beam, achieving this by using lasers for a new brightness level. To achieve the matrix function, to mask out specific areas of the street, we have used the 0.5-inch DMD from TI. Now you can find this technology already in the Audi e-tron. This is another example for an automotive projection application using DLP technology. Here we have designed a so-called picture generating unit for a head-up display. The PGU uses the 0.3-inch DMD from TI and is designed according to automotive requirements and is already in mass production since December 2016. A nice example of the combination of projection and imaging technology you see on this slide. Here we designed together with our customer a complete LiDAR using infrared laser diodes and MEMS technology for projecting and imaging. Now I would like to take a look into new automotive applications. Here I would like to introduce dynamic ground projection. As I'm sure of you are aware that this is a projection from the mirror or the door sill onto the ground for interaction with the driver or for vehicle-to-pedestrian communication. The new trend here is that the static projection with a gobo projector now is going to be replaced by a dynamic projection using, for instance, TI technology. TI is supporting this by introducing a new DLP chip optimized in packaging size and enabling cost-efficient design for image and video projection. From our side, we have already done some first concept studies to optimize brightness and installation space. We also looked into the strong tilted projection plane and made some evaluation how we can deal with it. On this slide, you see another new trend. It's in-car projection used for entertainment, advertisement, and autonomous car communication. It is used, for instance, on the front window for instrument cluster replacement, inside the car for information display on the interior, or on the back or side window for interaction with potential customers, driver greeting, or vehicle-to-person communication. It can be even used for advertisement, which is also a very common idea to use this. The projection is based on LED, the TI DLP chip, and the Jabil optical module. Of course, and that's the challenge, it requires automotive-grade projectors. And here we already have some experience. What is also possible is the interaction with gesture recognition. So that's an option which is also feasible. What we can offer here, projector design for automotive HUD based on 0.3-inch DMD is already in production and could be modified also for this application. We have also done a concept study for an automotive projector using the 0.5-inch DMD. And we also considered the use of holographic optical elements within these applications. Let me summarize our offerings. You can leverage Jabil's automotive programs in automotive optics. We can offer you the use of our capabilities, DLP technology, and this is more than 25 years experience in optical design for DLP. And Jabil can offer you a very huge manufacturing capabilities, also tailored for complex optical and electromechanical systems. I hope I could give you some interesting overview about Jabil and projection technology for automotive. And if you have any questions, I'm looking forward to receive it. Thank you very much for giving me the chance to give this talk, and please do not hesitate to contact me in case of questions.
All right. Thank you very much, Mr. Huntke. I have a question for you. There is a Jabil in Israel. Are you in contact with them?
Yes, we are in contact with them. Jabil is a big company, as introduced on the first slides, and the team here in Jena, of course, is mostly supporting these design projects, and we are even working with Israeli companies. I think it's not a secret that the LiDAR I showed on the slides is the one from Innovis. We had a talk today in the morning, and our team is working with them. Yeah.
Okay.
And currently in Israel, we have a small production site located.
Yes. Okay. Ladies and gentlemen, the Q&A time now, please.
What about imaging systems?
So imaging system, basically, I mentioned this in my talk. Our focus is on DLP for automotive. Here we are building or designing projection modules or optical engines, but we also have experience with MEMS, LCOS, and other systems. Or what does this answer your questions? What could you give me a little bit more insight?
The question was from Frank. Frank, do you want to explain?
Yeah, so I quickly unmute myself. Hello, Mr. Huntke. Yeah, I'm wondering if you're also covering, let's say, optical systems for camera systems for automotive applications in Jena, for example.
So for camera system, we have capabilities and we support this with the team in Burlington. They build active alignment machines. So that's basically we have the capabilities. Nevertheless, as I mentioned before, Jabil is not a product provider, so you can, if you give us a spec, we don't have off-the-shelf cameras are available. Yeah? So our target would be to design something for you according to your requirements.
Okay, any more questions? All right. So thank you again, Mr. Huntke.
Thank you.
And wish you a success, of course. Let's go to the next one. Mr. Dani Atzmon leads the R&D at Cognata Israel. Mr. Atzmon will speak on the autonomous driving and ADAS simulation platform driven by artificial intelligence. I'm very thrilled to hear this lecture. This is a different aspect of the automotives. We are talking about simulation. Okay, so let's go, please.
Hello, everybody, and thank you for attending my lecture. My name is Dani Atzmon, CEO and founder of Cognata, a simulation company from Israel. And today I'm going to cover in my lecture about our new technology called Real-to-Sim. It's a large-scale sensor simulation for ADAS and autonomous driving systems. A little bit about Cognata. We were founded 5 years ago. We are today more than 50 employees coming from very respectable companies in the industry. We raised more than $23 million from top-tier investors, and we have a lot of tier-1 partners that are supporting us. A little bit about the validation problem. It's an ever-increasing effort. If in the past, to validate an ADAS system, just a warning system, you need to drive some thousands of miles. Today it becomes millions of miles for level 2. And for level 4, for like full autonomous system, it's on the billions of miles. So it's like an exponential growth in the validation needs. In order to solve this challenge, we have 3 types of solutions: simulation, datasets, and validation services. The simulation, it's a full software in the loop playground where you're plugging in your autonomous stack or sensor stack to test it. We are supporting all the common industry standards like ASAM, OpenDrive, and OpenScenario out of the box. Datasets, it's for companies that would like Cognata to create or like operate the simulation for them. For example, create us just a dataset of Chinese traffic signs, pedestrians, or American traffic lights. Validation and services, it's a full end-to-end solution. We're taking the data from the actual drives, automatically annotating it, and testing that the KPIs of the ADAS or AV system were met. A little bit of how we distribute our product. So the first one is a local station just installed on your PC, and you can drive with that, hundreds of miles per day. When you want to expand, so we have a cloud solution when you can drive virtual billions of miles per day. And if before actual launch of the system, we have an hardware in the loop bench system which connects to the actual hardware and gives it the final proof before going into actual drives. In terms of technology, just in high level, we have 4 layers of technology: static, dynamic, sensing, and cloud. On the static layer, we're building full cities in 3D, and we're doing it utilizing off-the-shelf maps. We built with that digital twins of cities like Munich, Shanghai, and San Francisco. On the dynamic layer, we're adding the virtual agents, the actual drivers or pedestrians, and we're doing it by observing traffic cameras worldwide. Sensing is what we'll cover today, all the sensing modalities like radar, camera, LiDAR, ultrasonic and others. And cloud is how we are running with scale our solution. So today we will cover sensor simulations. As we said, the main modalities are camera, LiDAR, and radar. With the camera, we're doing something which is quite unique. We're using deep neural network to render our images, and I will explain how. Let me just, what you're seeing here is like, you're seeing it's like three separated screen here. On the right-hand side, you're seeing a real video taken from actual drive in Germany. It's from an open data called Kitty. On the left-hand side, you're seeing synthetic implementation of the same scene. This is how simulation used to look like. So everything is in place, but it doesn't look realistic, not the vehicles or like the vegetation or the roads. In the middle is Cognata, what we call deep net inspired sensor. And we're using a technology called transfer learning to make the synthetic patches look like the actual video. We are learning that, when offline, then rendering in real time using our deep net. And as you can see, the deep net inspired sensor looks like the actual video. So a kind of magic of turning synthetic created imagery into something that looks like the actual sensor. And we prove mathematically that you can use those images to train your model. On the LiDAR, we're doing also similar processes, a little bit different, I would say. Here we have like physical compatible models based on actual measurements that we took, and we can model any kind of scan path of a LiDAR. We're not like limited to symmetric or something like that. And here we will show you a collaboration that we have with one of our partners, Innoviz, which is the LiDAR provider of BMW. So here you see, first of all, the Cognata rendering, which is high quality. And then on top of that, the Innoviz LiDAR. Again, it's simulated, and you take this point cloud is fully annotated. The drive looks quite realistic, and utilizing that, you can remove a lot of training and validation hours and do it with no friction of the cost. The third modality is about radar. So again, we're sampling actual materials, and I will touch it, having their radar cross-section values, and we also do a multipath reconstruction. So we'll have like ghost targets. Now we'll improve the quality again. So you can see like the red and cyan dots are coming from the radar reflections, including all the ghost targets. And as you can see, quite realistic to the ones who are using radars. And this is what you would expect in real radar. Now, how do we do it? So we have simulated sensor characteristics starting from materials. Each material in Cognata, each object is divided into more than 50 materials, different materials for the taillights, for the windows, for the asphalt. And then we are cross-correlating it with actual measurements for each modality, if it's a radar or LiDAR. We do physical distortion modeling for stuff like lens distortion or rolling shutter for LiDAR. Here you can see a fisheye camera. And then we have the rendering, like I showed you with the deep net, with the camera, for example, or physical rendering like we're doing for the LiDAR. And you can see here the thermal camera, and this is a LiDAR. Now, this, like up until now, we talked how we take actual sensors and bring it to the simulations. Now we'll show how we are finding what is interesting in the world and bringing it to the simulation. Not only the sensor, but also what is interesting, what is like less common, and make the training and validation of my model better. So here we'll show like a brief video that shows how we take actual video on the right-hand side and bring it into the simulation. So we're using here a computer vision-based technology that takes all the data from the right-hand video and put it into the simulation. But not only that we get all the distribution and statistics of different objects from real life into the sim. So for example, after ingesting 1,000,000 miles, we can tell you, okay, if you want to make something that would kind of challenge your algorithm, let's put a lot of cyclists, let's put people on skateboards, on corkinets, etc., on tricycles, etc., and then you get something interesting to test your system with. So if we like summarize the process that we're doing, we're ingesting large-scale amount of data. We analyze what are the distributions of the data inside this data, and then we generate relevant data for training your algorithm, kind of like balancing the data. Just taking what is interesting, putting it there. Now, we have a variety. After we know what is needed to be generated, we have a variety of environments that we can pick from, a variety of object catalogs, all the possible traffic signs, all the possible traffic lights, cyclists, motorcycles, vehicles, all the types, thousands of those are available with different level of fidelities, rusty, not rusty, bent. So we can find a lot of combinations which are almost impossible to find in real life. And when you find in real life, you might have a failure. And then for each sensor generation, for each data that we are generating, we're creating ground truth. And for that, we have all kinds of ground truth, from 3D to 2D bounding boxes, lane line segmentation, instance segmentation, class segmentation, and others. Now, how can the synthetic data help you? So synthetic data is accurate and comprehensive, and the annotations are automatically done almost on the fly. The content is diverse and more, say, it's tailor-made to the actual distributions that you need. So we are creating a solution to the problem that we are presented with, whether that we are presented with actual data and we analyze ourselves, or you can come to us with a plan and we are fulfilling it for you. And of course, we are growing and recruiting from DevOps to machine learning engineers, to computer vision engineers, to full stack, to customer success and product managers. We are growing in all fronts, and you are invited to shoot an email and join us. Thank you. Now we'll go to the question section. Thank you so much.
Okay, Danny, I think that you have in a chat a question. Can you read it? Or...
Yeah. So, can you be a little more specific as to the deep neural network technique used, GAN, which is generative adversarial networks? Also, did I understand correctly that it takes the models with materials as input? So the answer to both of these questions is yes. We're using to the style transfer technique, unsupervised learning techniques like generative adversarial networks. And secondly, for some of the models, we're using the material models, for example, for thermal cameras, radar models, and LiDAR, we're using the actual materials to model the sensor itself.
Is your product serving the regulatory authorities in Israel?
We are cooperating with them. Currently, there are still no regulations, but we are talking with the regulatory bodies in Israel, US, and Europe regarding how to certify an autonomous vehicle and what are the tests which are needed to make sure that you have what we call the virtual license plate. We cannot hear you.
Omer asked you, do you model the sensor noise?
Of course. And since we are taking actual measurements that are coming from real life sensor readings, we model the noise based on actual data that was collected and making it making the simulation very realistic.
Okay. And Frank asked you on the chat, are you also connected to the filming industry? They also have libraries of textures, etc., for backgrounds in movies. Just a thought.
Yeah, we're still not making movies, but I can tell that we have a lot of ex-movies industries working in Cognata for the 3D simulation and art.
Okay. Well, I personally am very interested in your technologies, and I think that it's very important development for the next steps in the autonomous vehicles. I'm sure they have to be trained and checked. But I think that there is one more question.
One more question in the chat, yes.
Okay.
Can you be a little bit more specific as to the DNN technique used? Example.
Yeah, I already answered that. We're using both unsupervised models like generative adversarial networks and supervised learning for some of the techniques. Yeah, like, and anybody which is interested to learn more can shoot me like an email and join the company. We're like currently 50 and going to like double the amount of employees this year.
We invite you to provide some lectures for the Engineers Association in Israel, and we will be in contact. Great lecture and initiative. Great.
Thank you, Tomo. Thank you.
So we'll go to the next one, Mr. Ira Sokiryansky. Ira Sokiryansky is the Vice President Product at Multiview Tech in Israel. Mr. Sokiryansky will speak on single sensor 3D imaging solution, multi-view 3D imaging solution, innovation and technology principle. So please. Ira, please.
"3D imaging is used by the world's most innovative industries. Let's take a closer look at the existing methods. These methods are complicated. They use multiple components that make assembly and calibration very difficult. They are also expensive, bulky, and utilize a lot of energy. Introducing Multiview's 3D imaging solution. Multiview uses multiple apertures in one lens to collect different viewpoints. The single CMOS image sensor accumulates the light passing through the system. State-of-the-art deep learning algorithms use the obtained raw data to generate a color image and a depth map. The Multiview solution captures color image and depth data in a single shot. The great news is, Multiview's solution can be easily assembled and calibrated in smartphones and many other ecosystems. It's compact, affordable, highly reliable, and energy efficient. Multiview's solution is poised to make an impact on a wide spectrum of market sectors: smartphones, access control systems, medical devices, automotive, drone navigation, IoT and webcams, robotics, and will greatly enhance existing 3D applications, 3D face authentication, augmented reality, object detection, gesture recognition, image refocusing, and more. It's the future, and it's here now. Multiview, simplifying 3D imaging.
A variety of in-cabin applications requires about 19 image sensors. Each sensor has different parameters: wavelength, field of view, resolution, color map, day and night vision. Existing solutions for 3D sensing are expensive and have a large footprint. For example, time of flight and structured light. What's next? Next is Multiview in-cabin camera, which has a wide range of required features and could be customized according to customers' requirements.
Okay, thank you very much. It's a Q&A time. Is there any questions? Okay, thank you again, Ms. Sokiansky. And we'll go to the last one in this session. We have another session later. And on this, Dr. Perlo is the CEO of IFEVS in Italy. Dr. Perlo will speak on low-cost sensing platforms for autonomous vehicles. He was supported by Dr. Nir Krasnikov in Israel. They are good friends. And please go ahead.
Good afternoon, this is Pietro Perlo, the chairman of IFES Manufacturing, and together with Dr. Krasikov, the head of the payload branch at NanoMotion, we will present the development we have on a low-cost sensing platform for autonomous vehicles. We will follow as much as we can the suggestions of the organizers, describing first our company, and the goals we have in terms of development towards autonomous vehicles. We will emphasize, of course, the development we have and the need to collaborate with other Israeli companies. Now, IFES was started in 2011. I was a former director at Centro Ricerche Fiat. We are focused on manufacturing safe, efficient, and let me emphasize, affordable electric vehicles. We start from 138 granted patent. We collaborate with a large number of R&D organizations in the manufacturing world. Our business model is very simple. We collaborate with national entities to produce electric vehicles. We are currently producing fleets in Italy, and we are addressing large-scale manufacturing in other countries. In Israel, in particular, the idea is having a manufacturing hub of innovative electric vehicles. In our factory, we develop passenger vehicles, vans, and bikes, and in the future also non-road vehicles. Now, the starting point is our van, which we already have and we are already producing at fleet level. The idea is to move from conventional vehicles to low-cost autonomous L4 level by 2024. And for this, we are already supported by a grant of the European Commission. Now, for this to be possible, of course, we have possibilities of, we need to satisfy many requests in terms of functionalities, and to satisfy all these requests, one single technology, of course, is not sufficient. We need a combination of lidars, radars, and cameras to get this, let's say, the performance needed for fully autonomous. Now, all of this, of course, is scaring in terms of complexity, because we have far-field visions, near-field visions, and we have side vision. We need park assistance and so many functionalities, which indeed require hundreds of people usually to develop the needed sensing platforms. Now, lidars and radars are relative sensing unit. And of course, this needs to be combined with advanced navigation solutions, including GPS. Clearly, this is a very high level of complexity. Now, let me provoke a little bit this conference, saying that LiDARs and radars follow the postulation of the extra emission theory, which we essentially raise emitted from the eyes. A theory that was endorsed since the 5th century before Christ, and that continued for some other 2,000 years. Now, with these, with LiDARs and radars, usually the sensing suite are composed of 20 up to 30 sensors, and this means complexity, high computation, and cost. Now, in our case, we are proposing an alternative, which is a more modern way of thinking, if you allow me this provocation, which is addressing a reduced overall complexity, reduced computational effort, increased performance, and first of all, reduced cost and the simplicity of installation. So what is this alternative? The alternative we are proposing is developed using an infrared and a visible sensing, scanning the horizontal and vertical axis. Looking at the performance of these gimbals, you see that we are starting from conventional cameras in the visible, and we are also using today cameras that are quite expensive in the infrared, but we have already understood what we can apply and already produced in Israel, by the way, replacing the current US sensors that are introduced in the gimbal. Let me emphasize that the gimbal are quite robust. They are already used in the military world, and they, of course, satisfy the standards, but still not enough for what we are addressing in the automotive in terms of ceiling and low cost development. Now, the peculiarity of this gimbal is that, of course, they scan the environment horizontally and also vertically, but they also do another thing. They can work together in couple, doing a triangulation. This has an implication in terms of simplicity of elaboration, because you start from an image and at the same time you also have a simplified interpretation of distance and size of object you are encountering. Now, looking at the overall performance of the proposed sensing platform, you can see that there is a human recognition at 900 meters, human classification at 400 meters. During this parallax I was talking about before, we can do some distance estimation, but also very important is that we have dual thermal and day sensing, which means that the visibility also in various climate conditions is absolutely acceptable. Another important aspect that performing optical flow analysis, we can also think that we can work in a GPS-denied environment. Now, as I was already saying, the simplification in terms of computation is indeed very promising, in the sense that we start from images and also from triangulations. Now, another important aspect for the automotive is that you should not only think in terms of the final L4 autonomy, but you can also go step by step, because simplified versions of these gimbals can be used for, let's say, a step-by-step approach in other systems. Now, how do we introduce the gimbals in our vehicles. The preliminary installations we were thinking of were gimbals outside the cabin, but we also have now a solution for gimbals inside the cabin, simplifying very much the development of the gimbals in terms of sealing properties. Very interesting is that the invisibility around the vehicle is very limited, which means that we can reduce very much the number of other sensors usually needed when applying LiDARs and radars. So altogether, the motivations we have to adopt this solution is the overall reduced complexity, reduced computational effort, high performance, lower cost, and simplicity of installation. We are essentially proposing what the animal world is doing, using eyes, combination of eyes, and eyes in movement together with the head. Essentially, we are propose a very sophisticated solution, which is a synthesis of simplicity, I would say. As Leonardo da Vinci was saying, simplicity is the last sophistication. Once we have installed the gimbals on the car, we need the car to be autonomous, which means that we need unsupervised learning techniques. This can be done using standard digital processors. In fact, there are already very advanced digital processing units available in the market for this. But there is also another opportunity, which is using a novel embeddable analog MRAM-based accelerator, which, according to our estimation, is 10,000 times faster than what the market is offering now. For this specific development, we are collaborating with the Moscow Institute of Physics and Technologies and other Israeli institutions. Now, what is the market potential? For sure, LiDARs and radars and other combination of multi-cameras will reach the market, are already in the market, and the expectation is that by 2025 platform use and let's say a plug and use platform will be available by 2025 at $4,000, $5,000 or even less, and this platform will be widespread by 2030. There is large opportunities in road vehicles and also air vehicles, of course, with various form of implementations. Here, the market is indeed expecting huge developments within this decade already. And of course, there is another big potential in wheeled and legged indoor and outdoor robots, where the most optimistic forecast probably will underestimate the reality. In terms of what it is needed in terms of funding, the sensing suite is already available somehow, but some further miniaturization and adaptation to the automotive world is needed. We also need funding to finalize the development of the MRAM-based ASIC. We also are asking some funding to experiment a fleet of autonomous Ivan in Israel. But we are optimistic people, and we think that through the microfactory, producing 50 vehicles a day from 2022, we can also support the development of the autonomous vehicle. Of course, the complementarity is foreseen with several Israeli institutions for that to be possible. Now, as a final summary, I would say we are proposing autonomous vehicles adopting a novel low-cost sensing unit based on gimbals. We are also proposing embeddable MRAM-based AI processors, which are 10,000 times faster than available unit. Very important, we are proposing a radical, novel approach to manufacturing high performance and affordable urban electric vehicles. The idea is to start in Israel producing 50 vehicles a day from 2022, aiming at becoming the producer of reference in the Mediterranean area. High strategic value for Israel because of the proposed high tech, because the impact on CO2 reduction, and also not secondary aspect, the impact on employment and the evolution of the local supply automotive supply chain. Thank you for your attention. You can contact me at the number he reported, but you can also contact Dr. Karasikov, who consulted me for the foundation of IFES Manufacturing Israel. Thank you once more.
Thank you very much, Dr. Perlo. And of course, thank you to the Dr. Nir Karasnikov. And it's a Q&A time. Please. I'm not sure that I understand where you are going to put the gimbal on the car.
Behind the windshield with a new sensor.
The windshield.
Yes, at the beginning of the conference, there was an introduction reporting to what the 3i is doing in Israel. We think that sooner or later we will get in touch with them to explore what their sensors can do with our gimbals. Yes.
Other try to tackle the problems of dust, fog, rain. What do you think with your instruments? How they can cope with it?
Once they are behind the windshield, I believe that the only thing you have to do is to keep the windshield a little bit clean. But we don't see any issue if they are within the cabin. But
the visibility will be limited. It's not because of the dust will reach the gimbal. The dust will it's on the other side.
Yeah, but this is what happens for every camera you have inside the cabin. This is there's nothing new for that. Yes.
And the SWIR the ability to have image at bad conditions is better because it's a longer wavelength.
Mm-hmm. Okay. Did you test it on the road to see what will be the range?
Not on the road, but Nir can refer to what it has been tested in other fields. Of course, this is not a road application.
So our playground is not the road, is other application, airborne, etc. And Dr. Perlo mentioned visibility of a person at 900 meters. I don't think it's needed. But the range is a few hundred meters, for sure equivalent to what was presented here for LiDARs.
Okay, all right. Okay, and other questions from the audience? Well, thank you very much.
Thank you, Shlomo, and everybody. Thank you, indeed.
And we are going to a recess. We will be back on 3:30 p.m. Israel time this afternoon. So be here in about half an hour. Thank you very much. See you all later.